Good evening everyone, this is Manas, your friend and tutor, and I'm back with another video on acceleration analysis of mechanisms. Today we are going to tackle this problem, and that's a toggle mechanism, and we are going to unleash with all the tools which we have learned in the previous two sessions. And if you haven't seen the previous video, based on and 4-bar mechanism, also the first video was based on a slider crank mechanism, and I explain you the entire concept behind a link, what sorts of accelerations are associated, a tangential acceleration, a centripetal acceleration, what are the formulas. You must watch all of those videos. Only then will you be able to understand what I'm about to comment on. Here we go. That's a toggle mechanism, right? The fixations are O, Q and G. Okay, now what we need to do, there are certain things which we need to calculate. With respect to the slider, we want to find its velocity. It's undergoing a sort of horizontal motion, isn't it? And then secondly, we need the acceleration of slider and angular acceleration of link BD. Now for all of these things to be accomplished, you first need to you first need to make the velocity diagram and then follow it up with an acceleration diagram. So 3 stages, config diagram, recreate this using a suitable scale, any scale of your choice, depends on how your fine sense of judgment works, and then follow it up by the velocity and acceleration diagrams. And here we go. So the first thing, this rotation is anti-clockwise, isn't it? This is 210 rpm, so you can convert this 210 rpm into omega. That can be done. So omega is 2 pi n over 60, simple. This is rotations per minute. We need radians per second. Here we go, 2 pi n over 60, that is rpm. Yeah, just do the math. V equals omega r. So we need the velocity of A relative to O. V equals omega r. Omega is 22 radians per second. R is the length of the link itself, 200 millimeters, that means 0.2 meters. Very simple. So that's the velocity's magnitude which we have got. Now for making the velocity diagram, we'll be using this scale. You can use some other scale also, right? So this is my choice, and if you want your answers to closely match my answers, you should be taking the same scale, right? So with that, let's proceed. Fixed points O, Q, G. Let's make a point O, Q, G. Velocity analysis. With respect to all the links, you have to make the perpendicular lines. You know how to make the perpendicular lines. You have seen that in the first video, right? Using a roller scale or using a drafter. I showed an animation to you. So if you haven't seen that, do refer to it. OA, since this is anti-clockwise, so the velocity's direction will be somewhere here, northwest. Yeah, right, roughly northwest. Okay, so perpendicular to this link OA, draw a line perpendicular to this link OA, which happens to pass through this point. Here we go, right? This is 50 millimeters. B with respect to A. So this link, now we have got point A, we need to locate point B. So point B's location can be worked out from A and from Q, right? A is known. So with respect to B, this A will be along this line, perpendicular to this link AB, perpendicular to this link AB. Somewhere here, we will find point B. B with respect to Q, this is in the configuration diagram. In the velocity diagram, it will be perpendicular, but passing through this Q. Perpendicular, but passing through this Q. And there you go, that's point B. This arrow will represent B with respect to A, and the arrow over here will represent B relative or B with respect to Q. Velocity diagram. What's left? Point D is left. That also can be worked out very easily. D's location with respect to B. This is the length of the link, perpendicular to that, passing through B, perpendicular to BD, passing through B. Somewhere here we'll have point D. D is sliding horizontally forward or backward with respect to G. So right now just make a line parallel. It is either forward or backward, just make a line parallel. It is going to intersect somewhere here, that's point D for you, and this arrow is D relative to B, and this arrow is D relative to G. Done. Velocity diagram done and dusted. What we now need to focus on are the calculations of centripetal as well as tangential acceleration, at least the ones which we can calculate directly. Now for this link OA, we know angular velocity, and this is the angular acceleration case. The previous problem, the Fubau mechanism problem, was based on a retardation case. Okay, so this is going to be slightly different. I'll tell you the difference between the two. Here, here we go. Let me just show that to you. Where is the table? Right, you need to do all the measurements like AB, like OA, BQ, DG, and so on. Do all the measurements in this table. How many vectors are there? 1, 2, 3, 4, 5 vectors, all of these vectors. So this was known to us initially, isn't it? So you can measure all the lengths like AB. AB will work out as something, then BQ will work out as something. So all of these lengths, using a scale, using a ruler, measure all of these things and write them in this table. This is what you get. Right? So these are the corresponding values in millimeters. Again, you can see I've written 16.9607. Well, hell, it's not possible for you to manually, using a scale, you cannot measure something as minutely as 16.9607 millimeters. It can only be implemented and extracted from a software. So I did this initially on AutoCAD. That's why I've got awesome, accurate values. You won't be able to do that. Only when you implement this on AutoCAD, then it's possible. If you implement this on a drawing sheet and if you're drawing it manually, man, never, this is never going to happen. You are going to, even if you're closer to the 16 or 17, you are on the right track. Don't worry, even 18 and 15 will do the job. Things happen, we are humans, we are bound to make errors. That's why we've created a computer, machine, which can do that job for us, which can do it accurately. Okay. Alright. See, watch. 50 mm equals 4.4 meter per second. 1 mm equals 4.4 divided by 50, which is 0.088. So all of these measurements when multiplied by 0.088 will give their corresponding values in meter per second, and this is exactly what you get. Here we go. That's it. Now, you know something. Centripetal accelerations, as I already told, is v square upon r. Tangential acceleration, it's a bit tough because alpha's value is not readily available, alpha r. So we have as many as 1, 2, 3, 4, 5 links. So for 5 links we have all the velocities. You can calculate this centripetal acceleration, but alpha cannot be calculated. Alpha can only be calculated for this link OA, I guess. Yeah, for OA you can calculate alpha, and for everything else you can't. Anyway, so we can move forward. We know all these values. Let me tabulate them properly. In one section I'll have all the tangential components. First of all, I'll have the radial components, and the other side I'll have all the tangential components. Let me show that to you. These two are elementary formulas in the environment of acceleration analysis of mechanism, and I would encourage you all to memorize them. Here we go. AO, centripetal tangential. Take BA, B with respect to A, centripetal tangential. Fine. BQ, B with respect to Q, centripetal tangential. And finally, D with respect to B, centripetal and tangential. And this D with respect to G is linear motion. No centripetal, no tangential. It is simply linear motion. Fine. V square upon R. Velocity AO, how much? 4.4. Plug it in. AO is 200, that is 0.2. Do the math. Alpha R. Okay, alpha is 60 radians. Alpha 60 multiplied by R is 200, that is 0.2. Done. Very easy. All the values are in meter per second square. Then let me show you one more. B with respect to A. Okay, the velocity B with respect to A is 1.493. So 1.493 square divided by BA's length is 0.4 meters. You see this? So similarly, all these values can be calculated. So let us now arrange all of this in a proper sense. Here we go. Let me show that to you. And this is much more appropriate. Here we go. These are all the radial components. These are all the tangential components. So only one tangential component is known, that is of link OA. Right? Alright. So that's how you do it. You can do the conversion also. Since you have to make the acceleration diagram, you need to have their corresponding values in millimeters. So use this. This is meter per second square. From meter per second square to millimeters. So multiplied by all of these, multiplied by 1.033. When you do that, this is what you get. That's exactly what you get. Alright, now with this we are going to start our quest for making the acceleration diagram, and here we go. That's the scale which we've chosen. 96.8 has been assumed as 100 millimeters. Okay, so the first thing is, this is the centripetal acceleration. Watch, fixed points O, Q and G. Done. In acceleration you write with in small letters O1, Q1, G1. Okay. This is centripetal acceleration. So obviously it is going to be parallel to the link. Parallel to the link, whether upwards or downwards, that is going to be decided referring to this configuration diagram. It is going to be towards O, that is downwards, towards O, this way. Okay, A with respect to now. This sometimes gets a bit trickier, but you should note it down. As far as tangential component is concerned, this is known to us. How much is it? This is 12.396. So 12 mm approximately, isn't it? So if it is the tangential component, it is perpendicular to this link OA, somewhere in this direction. Okay, here you can see that in the velocity diagram, or parallel to OA in the velocity diagram, you can say. So whether to go above or below, this is slightly confusing. If it is a case of acceleration, as in over here, it's a case of acceleration, go with this direction. Above. How much? 12.396. If it was a case of retardation, obviously the velocity would have shown in this direction, but the acceleration would have been exactly opposite. It would have been in this direction then. Once again, here it's a case of acceleration, so tangential acceleration will be in the direction of this velocity. Done. If it is a case of retardation, if this was a case of retardation, then this FTAO would have been in this direction. It's as simple. And if you have observed the previous problem carefully, you know what I'm talking about. Okay, so that's centripetal, that's tangential, and when you join O1 with this A1, that's the total acceleration. Done. So point A1 located. Wow, we should look for point B1. How to do that? So point B1, that's 5.753. This is radial. B with respect to A. Okay, with respect to A1. Draw a line, parallel this way. How much? 5.753. Very easy, this small line. Okay, now we don't know anything about the tangential component, so just with respect to this line, with respect to this link, make it perpendicular. Done. Somewhere along this line we are going to have B1. We don't know exact location. Okay, now B1 can also be located with respect to Q. With respect to QB, parallel, keep it parallel. Q is over here. Okay, keep it parallel. So it's going to be something like this. Let me show you here. Here it's going to be something like this, but whether to move this way or this way, that has to be, it always has to be towards Q this way. What is the magnitude? 40.24. This is the magnitude. Again, the tangential component, this tangential component will be perpendicular to the link like this. Done. That's the location, precise location for B1. Easy, isn't it? So that's B1. This is tangential BQ, and this over here is tangential B with respect to A. Tangential B with respect to A, tangential B with respect to Q, and that's the total acceleration. That's the total acceleration of BQ. Okay, now what? Anything else? A point D is yet to be worked out. So look at this, BD, parallel, centripetal, D with respect to B, how much? 20.35, parallel. Okay, where is B1? Parallel, this way, towards B with D with respect to B, towards B, left hand side. Okay, that's the magnitude, 20.35, and perpendicular to this we are going to make a line, and here we'll have the tangential component this way. Now D with respect to G is rather linear motion, and draw a straight line, parallel. this way, parallel, parallel, horizontal, horizontal, that's it. This point is your point E1, and this is ft dB, this is the total acceleration, and that's fd for you, linear acceleration of link T, you can say, or slider D, piston D, whatever. Now we are going to talk about calculations. So here we go, let me show that. It's going to be very easy, and now these data are going to be very helpful. Okay, so what the first thing which we need to work out, velocity of slider and angular velocity of link BD. Velocity of slider, this is D. Measure this, you are going to get the value as 28.5907. Again, if you get 27, 28, 29, whatever, take that, right? If you are implementing this on a software, you will be getting a very accurate value, just like mine. 1 millimeter is 0.968 meter per second squared. So multiply it, you will get the corresponding value in meter per second. That's the velocity. No, not 0.968. Well. This is velocity. For velocity, we have this scale. 1 mm is 0.088. Yeah. Now we are on the right track. Angular velocity. Now there are two approaches of calculating the angular velocity. Let me show you approach number 1. Can you work out what this is? Just look at the board. Centripetal acceleration. What is this link? D with respect to B. D with respect to B is equal to what? Omega square R. There is a formula V square by R, but there is an elementary formula which is omega square R. We want to find omega. So omega is equal to what? F C D B, and this is nothing but the length of the link. Length of the link is dB, and if this is omega square, if then the omega is going to be under root of. Yeah, there you go. Done. Plug in the values. FCDB. FCDB. This is B1. This is D1. FCDB. That's FCDB. Measure this and put it over here. Now this measurement guys, FCDB will work out as 20.359 mm, but this is in mm and this is from acceleration diagram. On multiplying that by 0.968, you are going to get the corresponding value in meter per second square. So do that, divided by length of BD. BD is 500 mm, that is 0.5 meters. Just do the math. So damn simple. Approach number 2, V equals omega R. So omega equals V over R. Omega for BD, V dB upon BD. Yeah, it's quite simple. VD with respect to V. D with respect to V. Measure this. Measure this. What you get is 35.6721. Now this is velocity. We have this scale. This is in millimeters. Multiply by 0.088 and then divide by length of the link BD. BD is 500. That is 0.5 meters. And that's it. You're going to get the same answer. Quite obvious. Finally, second part of the question. Here we go. Acceleration of slider and angular acceleration of link BD. Okay, watch. Slider D with respect to G. Okay, acceleration of slider. So where is D with respect to G? Yeah, here it is. FD. Measure this length and this should precisely work out as 16 millimeters. So mm into this is 0.968, multiply it, and this is the corresponding value in meter per second square, that is FD. Angular acceleration can be worked out from tangential acceleration. You know tangential acceleration. Look at the board. Ft is equal to alpha r. Alpha is equal to tangential acceleration over the length of the link. This is what we are going to use. So damn simple. Here we go. By BD. Okay. So for link DB we are talking about D with respect to B. FTD with respect to B. Where is it? DB. FTD with respect to. Measure this. On the measurement you are going to get this value 57.3. Right. This is in millimeters. This is acceleration. So multiply by 0.968. Going to get the corresponding value in meter per second square. Divide by BD length. So BD length is 500 again. So that's 0.5 millimeters, 0.5 meters, and that's it. That's it. Anything else? Anything else? Are we done? Yeah. Let me show you what's in the next lecture. We are going to tackle this problem. It's an Andrew variable stroke engine mechanism. It's going to be fun. So So guys, that was all for today. I'm going to see you again in the next video. Until then, take care, have a nice day, keep learning, keep watching. Thank you.